Great, thank you so much, Mr. Chairman, and greetings from Portugal. My name is Raul Campilho. I'm here to share a work which is entitled Experimental and Cohesive Zone Evaluation of Adhesive Joints in 3D printed structures under tensile load. This work was a collaboration between ISEP and INET Porto. And here we can see the structure of the presentation, which has mainly the statement objective, a short contextualization to the topic of all of this involved, and then the mental and numerical work, comparison of the results, and finally the conclusion and some suggestions for future work. The main objective of this work is to experimentally and numerically analyze adhesive joints between polymeric 3D printed adherents. And with that goal, we will first estimate the properties of different materials. We are going to test three different adherents, also study the adhesive joints, and then evaluate the geometrical and material effects on the strength of this bonded joint. A short introduction to additive manufacturing. We know that there are 7 main categories of additive manufacturing, but between of these, the PVF and FDM processes are usually the most common, and here we are addressing FDM process. The main problem of additive manufacturing is the size of the components, so one possible solution is to manufacture smaller parts and then use a suitable joining method so that we can join the parts. And within this scope, we have adhesive joints, which are a technique used for structural connection, which is used in different sectors, and it has both its advantages and disadvantages. The combination between these two technologies allow us to surpass the size limitation of the 3D printed, but to that we need to have numerical techniques that allow us to quickly design this type of connections, which can be done with different methodologies. In this presentation, I will approach the cohesive zone modeling technique for static modeling, and we will evaluate different types of joints with different adherent types, namely PET, ABS, and PLA, and also 2 adhesives. Beginning with the adherents, we are considering these 3 polymeric adherents. Here in this slide, in this table, we can see the fabrication conditions, including the temperature, printing speed, layer height, in steel, which was 50% in all of the cases. And of course, that to analyze the adhesive joints, we first needed to evaluate the mechanical strength of the different adherents. With that purpose, we carried out tensile tests to bulk specimens. We can see the failed specimens that were tested in our experimental run. We considered a testing speed of 5 millimeters per second and a mechanical extensometer that allows us to obtain the stiffness accurately of all of the materials. Here we can see the comparison between the 3 adherents in terms of load displacement curve. The PLA resisted to the highest load, as we can see, but it has a brittle behavior, while the PEHG and ABS had a smaller load to failure, but they have a higher deformation before failure. In this table, we can evaluate the properties that we obtained, namely the failure load, the maximum stress, the elastic limit, the strain at failure, and the Young modulus, which will be valuable in our numerical models that we'll present further. We consider 2 adhesives. One, the LD 2015, is an epoxy adhesive, and the Stick-A-Force is a polyurethane adhesive. The Stick-A-Force is more ductile but less strong than the 2015, so we are going to test 2 contrasting behavior when implemented to join these 3D printed components. In terms of experimental part, we consider three types of joints under tension: a single lap joint, a single step joint just with one step, and a scarf joint. And in all of the cases, we consider three overlap lengths, which are signaled by LO in the figure, between 5 and 20 millimeters. Some details about the fabrication process of the adherent, details also of the preparation of the adhesive and the bonding process, and surface preparation, one example for a start joint before sanding and after sanding. The specimens were tested. The testing speed was 1 millimeter per second in all cases. We had two types of failures depending on the geometry and material, cohesive in the adhesive layer, but also adherent failure, as we have two examples at the right, two examples of adherent failure, which takes place particularly at higher overlap length. And here some details about different failure modes. We have some cases with cohesive failures in the adhesive and other cases with failure in the adherent. All the p-delta curves were collected for the three types of geometries, and here we present the results divided by joint type. For the single lap joint, in terms of adherence, the PLA shows the highest strength joint, followed by the ABS and PHG, and regarding the adhesive, the 2015 with lower overlap length gives the best result, but as we increase the overlap length, the 7752 approximates to the former adhesive because of its ductility. In terms of overlap length, its increase always causes an increase of maximum load, since the failures were mainly in the cohesive of the adhesive. In terms of step adhesive joints, in terms of comparing the adherence, we saw that all materials have a very similar strength. This is because most of the failures in the adherence, because of the brittling factor of the adherent due to the shorter cross section with the step geometry, and between adhesives, the 2015 showed better results than the 7752. In terms of overlap length, the increase didn't affect values because of the fact that failure took place in the adherence mainly. Finally, for the scarf joint, we saw that in terms of adherence, the PLA was the material with the highest strength, followed by the other adherents, and between adhesives, the 2015 gave the best result. But as we saw with the single lap joint, by increasing the overlap length, with the 7752 approximates the failure load due to its higher ductility. And finally, regarding the overlap length, we also have an increase of overall strength with this parameter when in the cases that we have failure in the adhesive. These simulations were carried out to corroborate the CZM or the cohesive zone modeling ability to model the experimental behavior of the joint, so to have a numerical framework that we can use to expedite the design. And here we have some details about the model. For example, the triangular mixed mode cohesive law that we use to calculate the adhesive, and details about the boundary one clamping and another tensile loading at the other joint, and also representative matches of the joints for the single, for the step joint, and for the scarf joint. Here we see the comparison between failure modes, experimental and numerical for the single lap joint. Each column is one type of analysis. We have experimental and numerically, and we also have the three adherents. We can conclude that between the two possible failure modes and cohesive, we have a good agreement. There were some exceptions. For example, the joints with PLA and 2015, they have a different failure mode, but in the end and overall, we have a good representation of the failure mode between the experiments and numerical simulation. In terms of maximum load, the numerical analysis provided highest strength by approximately 10%. The PLA gave us the best result of strength, and the adhesive 2015 also gave the best result compared to the 7752. As we see in the graphics, increasing the overlap length, which is in the x-axis, we also have an increase of the maximum load as the failures were mostly adhesive. On the other hand, step joints, we also have a good agreement between failure modes. There was just one exception, which is the PLA joint with 7752 and flap length of 20 millimeters. And in terms of maximum load, as we said before, there are no differences or no statistically relevant differences between different overlap lengths because failures were inadherent. Once again, the numerical analysis overstood the experiment, in this case, by an average value of 9, and the step joint with an ABS shows similar strength with a slight difference to PETV. The last type of
Raul,
joint, yeah,
Raul, sorry if I interrupt you. You have 1 minute
no
to
problem.
conclude. Thank you.
Okay, thank you. The final type of joint is the scarf joint, and in this case, we have a good agreement between the experiment and the numerical simulation step for two particular joint configurations. In terms of maximum load, we can see that we have a large increase between 5 and 10 millimeters of overlap, but between that and 20 millimeters, we had a stabilization of the maximum load because of the failure shifting to a failure in the adherence. Here, I would like to summarize the conclusion. The best results were obtained for the 2015 in terms of maximum load. In terms of adherence, the best results were for the PLA, which had also the highest strength and stiffness of the bonded set. And in terms of maximum strength, we were always below a difference of 10%, which leads us to conclude that we can use this technique for the evaluation of 3D printed bonded joints. I would like to finalize with some future work proposals, and thank you so much. I finished my presentation.